I would now like to deal with inductors in parallel, and as always, the basics are going to remain exactly the same. So in front of you, I've got a simulator that's going to have a single inductor that gets charged through a series resistance. And if I was to quickly go and do that simulation, you can see the magnetic field and the voltage and all of the interaction on the right-hand side. I'm using abnormal values, but that's just because I want to get the graphs to give me a meaningful image. As you would know, as soon as you put a voltage across an inductor, you're going to measure the full voltage drop across it, and then as the magnetic field collapses, so the voltage drop is going to change, and that is going to be typical for all inductors. So for a single inductor of 600 Henry, at least 6,000 Henry, that is the image that we would get, and I'm going to go and capture that image quickly. And my image has been put up on the screen. The time constant for a resistor and an inductor is calculated as the inductor value divided by the resistance. Now what I'm going to go and do is I'm going to take the same inductors and I'm going to put them in parallel with each other. Inductors in parallel are calculated the same as resistors in parallel. So if I was to have an inductor in parallel with another inductor, and let's go and call that L1 and L2. We can say that L total is going to be L1 times L2 over L1 plus L2. And always put that in brackets if you want to, if you're using a calculator, which is going to give me a value of, now each of those are going to be 6,000 Henry. So I'm going to have 6,000 times 6,000 divided by 6,000 plus 6,000, and that should give me a total of 3,000 Henry, which I can now go and put in my simulator. So there I put in, at least I haven't, I'll try to, I'm going to go and put in the 3,000 Henry. Is that going to take? Yes, I'll go and put in the 3,000 Henry. And if I was to go and simulate that, look at the image on the right-hand side, and what you should see is that the time is going to change. Now, it's a smaller inductor, and therefore the time is going to be a lot shorter. So this just shows me the equivalent of having a circuit with two inductors that are going to be in parallel with each other. Let's go and copy the image. And there you have the two images side by side. On the left-hand side, we've got a single inductor of 6,000 Henry. On the right-hand side, we've got the equivalent of two of those 6,000s that would be in parallel with each other, which gives me a total inductance of 3,000 Henry. And as you can see, the smaller inductance is going to result in a smaller time for the graph itself. Again, as an engineer, you deal with so many different things and you wouldn't be expected to remember all of this, but you know where to go and get your resources just to refresh your knowledge.